At the end of this video, you should be able to distinguish between a quantity, a unit, and a measurement standard, name and use SI units for length, mass, time, volume, and density, and distinguish between mass and weight. Chapter 2, Section 2, Units of Measurement. Measurements are quantitative information. A measurement is more than just a number, even in everyday life. Suppose a chef were to write a recipe listing quantities such as 1 salt, 3 sugar, and 2 flour. The cooks could not use the recipe without more information. They would need to know whether the 3 represented teaspoons, tablespoons, cups, ounces, grams, or some other unit for sugar. Measurements represent quantities. A quantity is something that has magnitude, size, or amount. A quantity is not the same as a measurement. For example, the quantity represented by a teaspoon is volume. The teaspoon is a unit of measurement, while volume is a quantity. A teaspoon is a measurement standard in this country. Units of measurement compare what is to be measured with a previously defined size. Nearly every measurement is a number plus a unit. The choice of unit depends on the quantity being measured. Many centuries ago, people sometimes marked off distances and the number of foot lengths it took to cover the distance. But this system was unsatisfactory because the number of foot lengths used to express a distance varied with the size of the measurer's foot. Once there was an agreement on a standard for foot length, confusion as to the real length was eliminated. It no longer mattered who made the measurement, as long as the standard measuring unit was correctly applied. Scientists all over the world have agreed on a single measurement system, called the International System of Units, abbreviated as SI. This system was adopted in 1960 by the General Conference on Weights and Measures. SI has 7 base units, and most other units are derived from these 7. Some non-SI units are still commonly used by chemists and are also used in this course. SI units are defined in terms of standards of measurement. The standards are objects or natural phenomena that are of constant value, easy to preserve and reproduce, and practical in size. International organizations monitor the defining process. In the United States, the National Institute of Standards and Technology plays the main role in maintaining standards and setting style conventions. For example, numbers are written in a form that is agreed upon internationally. The number 75,000 is written 75 space 000, not 75,000, because the comma is used in other countries to represent a decimal point. The 7 SI base units and their standard abbreviation symbols are shown on the screen here, but also in page 34 of your text. All the other SI units can be derived from these fundamental units. Prefixes added to the names of the SI units are used to represent quantities that are larger or smaller than the base units. The table on the screen here, which can also be found on page 35 of your text, lists SI prefixes using units of length as examples. For example, the prefix centi, abbreviated lowercase c, represents an exponential factor of 10 to the negative second, which equals 1/100th. Thus, 1 centimeter, or 1 cm, equals 0.01 meters, or 1/100th of a meter. The SI standard unit for length is the meter. A distance of 1 meter is about the width of an average doorway. To express longer distances, the kilometer, represented by lowercase k, lowercase m, is used. 1 kilometer equals 1,000 meters. Road signs in the United States sometimes show distances in kilometers as well as miles. The kilometer is the unit used to express highway distances in most other countries of the world. To express shorter distances, the centimeter is often used. From Table 2-2, which is also found on page 35 of your text, you can see that 1 centimeter equals 1/100th of a meter. The width of your textbook for this course is just over 20 centimeters. As you learned in Chapter 1, mass is a measure of the quantity of matter. The SI standard unit for mass is the kilogram. The standard for mass, defined in Table 2-1 or 2 slides ago, is used to calibrate balances all over the world. The mass of a typical textbook is about 1 kilogram. The gram, represented by lowercase g, which is 1,000th of a kilogram, is more useful for measuring masses of small objects, such as flasks and beakers. For even smaller objects, such as tiny quantities of chemicals, the milligram, represented by lowercase m, lowercase g, is often used. 1 milligram is 1,000th of a gram, or 1/1,000,000th of a kilogram. Mass is often confused with weight because people often express the weight of an object in grams. Mass is determined by comparing the mass of an object with a set of standard masses that are part of the balance. Weight is a measure of the gravitational pull on matter. Unlike weight, mass does not depend on such an attraction. Mass is measured on instruments such as a balance, and weight is typically measured on a spring scale. Taking weight measurements involves reading the amount that an object pulls down on a spring. As the force of Earth's gravity on an object increases, the object's weight increases. The weight of an object on the moon is about 1/6 of its weight on Earth.
The mass of an object depends on the amount of matter the object contains. As long as the amount of matter remains constant, so does the mass of the object. The weight of an object depends on the force gravity exerts on it. Therefore, if the force of gravity on an object changes, so does its weight. The weight of an object depends on gravity. Changing an object's location will change its weight. For example, consider an astronaut who has a mass of 80 kilograms. On Earth, this astronaut weighs 784 newtons, but on the moon's surface, where the force of gravity is only 1.6 meters per second squared, the astronaut weighs 131 newtons. The astronaut's mass, however, remains the same on Earth or the moon. Weight can be measured using a spring scale. The spring scale measures the force exerted on an object by gravity. The weight of an object is expressed in newtons. Mass is measured using a balance. A balance uses a comparative mass on a lever arm to determine the mass of an object. The mass of an object is expressed in kilograms.
Many SI units are combinations of the quantities shown in Table 2-1, which again is on page 34 of your textbook or on the screen again here. Combinations of SI-based units form derived units. Some derived units are shown in Table 2-3, which you can find on page 36 of your textbook, or again on the screen here. Derived units are produced by multiplying or dividing standard units. For example, area is a derived unit. It is length times width. If both length and width are expressed in meters, the area unit equals meters times meters, or square meters, abbreviated lowercase m squared. The last column in Table 2-3 here shows the combinations of fundamental units used to obtain derived units. Some combinations of units are given their own names. For example, pressure expressed in base units is actually kilograms per meters second squared. The name Pascal, abbreviated capital P lowercase a, is given to this combination. You will learn more about pressure in Chapter 10. Prefixes can also be added to express derived units. Area can be expressed in centimeters squared, or square centimeters, represented by lowercase m squared, square millimeters. Volume is the amount of space occupied by an object. The derived SI unit of volume is cubic meters, represented lowercase m cubed. 1 cubic meter is equal to the volume of a cube whose edges are 1 meter long. Such a large unit is inconvenient for expressing the volume of materials in a chemistry laboratory. Instead, a smaller unit, the cubic centimeter, represented lowercase c, lowercase m cubed, is often used. There are 100 centimeters in a meter. So, a cubic meter contains 1 million cubic centimeters. When chemists measure the volumes of liquids and gases, they often use a non-SI unit called the liter. The liter is equivalent to 1 cubic decimeter. Thus, a liter, represented by a capital L, is also equivalent to 1,000 cubic centimeters. Another non-SI unit, the milliliter, represented lowercase m capital L, is used for even smaller volumes. There are 1,000 milliliters in 1 liter. Because there are also 1,000 cubic centimeters in a liter, the two units, milliliter and cubic centimeter, are interchangeable, which is very useful for you to take note of.
Volume is defined as the amount of space occupied by an object. The volume of a solid, like this cube, may be measured in cubic meters or cubic centimeters. The volume of a liquid is often measured in liters or milliliters. 1 milliliter is equal to 1 cubic centimeter. The volumes of irregularly shaped solids can be measured by the amount of liquid they displace. For example, this rock's volume can be measured by dropping it into the graduated cylinder and reading the new liquid level. The volume of a gas can be measured by measuring the volume of the container it is in, because a gas will expand to fill its container.
Liquids have adhesion. Water, for instance, adheres to glass. This creates a meniscus and slightly complicates the measure of the volume of liquids in a graduated cylinder. Water forms a meniscus, and the liquid curves up the sides of the graduated cylinder. To measure the volume of water in a graduated cylinder, read the value at the bottom of the meniscus. The picture shows a value of 9.5 milliliters. A smaller graduated cylinder creates more curvature in the meniscus than a larger one. Mercury forms a concave meniscus and the liquid curves down. To measure the volume of mercury in a graduated cylinder, read the top of the meniscus.
At this point, you should be able to distinguish between a quantity, a unit, and a measurement standard, name and use SI units for length, mass, time, volume, and density, and distinguish between mass and weight.